Okay, so this was the last lecture. If you recall, we were discussing inverter, and we were looking at the delay of an inverter, simple inverter with a resistor here. And what we said was the delay comes about because when I apply from VDD to 0, when I switch the input, the output is supposed to go from 0 to VDD. It needs to charge this particular node, and the node that the transistor switches off, the moment you go to 0, the transistor switches off, and so there is a simple R here and a C here, and it's a simple RC charging. And the issue was, I'd taken all of these different capacitors I've shown you now, that there's between gate and drain, and there is between drain and body. Body is ground, and between gate and drain here, and between gate and source here. So if I look at all the capacitors at this particular node, gate to body also, I've added it together. So in the last lecture, I'd sort of very quickly gone over it, and some students had issues with how can I take all these capacitors that are there and lump it into one single capacitor CT, which is between this particular node and ground. And that's a valid point, because I see a capacitor connected between here and here. There's a capacitor connected between here and here. There are only two capacitors or three capacitors which are connected between this particular node, output node, and ground. CDB1, CGS2, and C gate to body 2. So three capacitors are there. But what about these? How come we can, we were writing, I've included a gate to body also in the expression here. How come we are writing all of these with respect to ground? So yes, this is an approximation. So let's look at what is happening. If I look at a charging, so there is a charging current, whatever charging current comes from here. So that will be equal to dQj by dt. General charging current, so it supplies charges on various capacitors. Whether the capacitor is here, 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 or whatever, it has to supply the charge, the change in charge, dQj by dt, whatever is the charge. Now I can write these things, you can see here, for every capacitor, assuming the capacitors are constant for a moment. Capacitors are also, note that, functions of voltage, and voltage is changing. So, but for the moment, let's say capacitors are constant, so I can write it in this form. So if you look at CGD1, CGD1 is charging can be described as I equal to CGD1 multiplied by the effective voltage between these 2 points. D VD1 drain 1 minus gate 1 by dt. That's the net voltage across this particular capacitor, so that's how it charges. Similarly, CG2, gate to drain 2, we can describe it as VD1 minus V drain 2, the drain of the second transistor, by dt. CDB1 is fine. It is between here and ground, and CGS2 and CGB2, they're all between ground. So those are okay. So that's how the charging current is actually can be written. Now what we can do is, we can take dVd1 by dt out here, dVd1 by dt out, and write it expression in this form. Right? So it's simple rearrangement. Now of course, note that if I look at, for example, this one, the gate voltage is immediately brought to 0 and the drain voltage is changing. So if I look at during the transient, dVg1 by dVd1 would be what? Note that drain voltage is changing with time. Drain voltage, this node is charging, and this voltage is immediately, once the transition takes place, this is constant. So dVg1 is 0. It's not changing. It's not 0. So effectively what we can do is, during the transient, we can put this sort of term to 0. But note, if I include the transition, right? So if I include the transition, so if you look at this particular capacitance before the transition occurred, before VDD, before I did the input transition, the voltage here was VDD. The voltage at this particular node was VDD, and the voltage at this particular node was 0, right? VDD and 0. Now after the charging is complete, what is the voltage? Here it's 0, and here it is VDD. So what is the effective change in voltage across this particular one? Effective total change of voltage across this? 2 VDD, everybody sees the effective change. So the current here has to supply that charge here, equivalent to what? Some capacitance multiplied by 2 VDD. So it's not really DVG1 by DVD1 is if I include the transition also within my this thing here. So the effectively, if I look at some on an average, what I can say is that this particular, so note that M1, again, as I said, these transistors are going from linear to cutoff, M2 is going from cutoff, saturation, linear, and all that. This term effectively I can say is -1, so that the contribution of this term is 2 CGD1. Please realize why I'm saying 2 CGD as an approximate measure. Why I'm saying it? Because initially this node is VDD, this is 0. After the charging is complete, this is 0 and this is VDD. The net change in voltage across the capacitor is 2 VDD. And so the total charge that has to be supplied to this particular capacitor is CGD1 multiplied by 2 VDD. Right? So it's not just the CGD1. So that's why many times you will see in books and all that, what they do is they will put this as -1. So -1 here, and they will put this as 2 CGD1 on an average. There's not, on an average, you can say the contribution of CGD1 is twice because of this one here. Similarly, note that DVD2 by DV, if you look at CGD2 here, right? If you look at this one here, so initially this node is VDD and this node is ground. And then finally this node becomes VDD and this node becomes ground. So effective change here is also twice VDD. So in some sense, it's like putting -1 here. So -1 plus, so you get 2 CGD2. And this kind of a thing you would realize in Miller's effect when we discussed. In E210, Miller's effect was any capacitor connected between here and here gets multiplied by the gain of the 1 plus AV. So what is an average gain of this particular one? If you look at it, on an average, the gain of an inverter is -1. As you go from 0 to VDD here, this goes from VDD to 0 here. So the gain on an average of the inverter is -1. So if you look at Miller's effect, any capacitor which is connected between here and here gets multiplied by Miller's effect. So it will become CGD2 multiplied by 1 minus AV. AV is the gain, average gain. So that is also -1. So it's like 2, twice of CGD2. But of course, things are more complicated. On an average, you can write this as maybe 2 CGD1 and 2 CGD2. And then CDB1, CGS2, CGB2 remain as they are. But each one of them, note that the other complication is each one of them is sort of changing with voltage. This is changing with voltage. CGS2 is changing with voltage. Why? Because M2 goes from cutoff to saturation to linear. In cutoff, CGS2 is something else. In saturation is something else. In linear, it's something else. So each one of them is changing. So things are more complicated. So what we are saying is you can see if I put here -1 and put here -1, effectively I can write this as I equal to some capacitance CT times dVd1 by dt. And that's the motivation for writing like this. But note that these are all capacitors that I'm writing here. These are all some average values. These are not the instantaneous values are all changing. They're all changing with time. All right. So because of analytical calculation, we want to get a equation. So we're sort of writing it in this particular form. So accurate values of, again, delays, which takes into account all the changes, and there will have to come from simulation. But as a first order analysis, you can see why one is writing it as I equal to one single capacitor here. So the motivation for this is, once we write it in this particular form and put it here -1 and some sort of -1 here, they all add up into one single capacitance times dVd1 by dt. And dVd1 is what? Between this node and the other node is ground. So that's how all the capacitors get lumped up in one single place here, CT. Okay. All right. So now note that we are talking about a resistor, right? So we discussed the inverter in the form of a resistor here. But then similar things will hold if I replace the resistor by some other element. And we have been saying that the role of the resistor is to pull this particular node to VDD. The role of this resistor is to pull it up to VDD. The role of the NMOS is to pull it to ground. So this node, remember, any node in a digital circuit, any node is either 1 or 0. Now, if it is 0 and you want to change the state of the node, somebody has to pull it up to 1, right? So that's the role of the pull-up stage here, whatever that pull-up stage is. And if this is 1 and you want to pull it down to 0, then you need a pull-down stage to pull it down to 0 here. In this case, it's an NMOS transistor here. So our discussion is actually general. If we think of a delay, so look at now, instead of a resistor, I just put some pull-up element, whatever that pull-up element is, resistor, transistor, whatever you can think of, is a pull-up element here. So a slightly more general expression for current, for delay here. So when you go from VDD to 0, when you're talking about low to high delay, so you're going to pull this up to VDD. So we're talking about low to high delay. This is what it is, tau p LH, low to high delay here. So now so you are switching off this transistor, you go to 0, this transistor is off, and what happens is there's a current that starts coming in from VDD. This current starts coming in and starts charging the capacitor. So what we have is I equal to, we call this as pull-up current that comes from pull-up, equal to CT dV out by dt. As a general, because this is off. And therefore, what I can write is in general as tau p LH equal to, what tau p LH is. So I take dt on the other side, CT by IPU, and I do it here. And we are looking at tau p LH by definition is from 0 to 0.5 here, 0 to 0.5 VDD. So that's tau p LH. Now, what we are saying is, in a simple case, we are saying, well, we can define some average CT and some average IPU. This symbol is for average. So as a, one needs to look at CT as a function of voltage we have seen. IPU, the charging current, will also be a function of voltage. So if you want accurate expressions, you'll have to put in all the functions of voltage and all that and get it. But as a simple expression, what you can think of is tau p LH is 0.5 VDD. So take this term out and call it as some average capacitance by average pull-up current. Multiplied by what? 0.5 VDD. So as a very simple expression for what is a low to high delay, think of this particular expression here. You'll find this expression being used at several places in order to understand delay. See, simple expressions help you to understand and make changes and things like that, come up with new ideas. Complicated expressions are not that useful. For accurate expressions, go to a simulator and get the correct, the precise values of delays. All right. So this expression is very important because it tells you why there is a delay. Why there is a delay? Because there is a capacitance at this node, and CT. It has to be charged up to what? It has to be charged up to 0.5 VDD, from 0 to 0.5 VDD. And how much current do I have available? So simply you can see delay is nothing but charge divided by current. How much charge do I have to supply and how much current do I have? So on an average, how much current can my pull up on an average, as it goes from 0 to VDD by 2, it may be that the pull up current varies. Initially is high. If it's a resistor, note that initially the current would be high. And as this capacitor charges, the current will decrease. So current is in general a function of voltage, but you can define some average current over the transition. And you can define an average capacitance over the transition. And talk about tau p LH is 0.5 CT VDD by IP. Alright, now this is what I was saying, that in this case, if you look at a resistor, the current, if I look at pull-up current, when it's 0, the pull-up current is VDD by RD. Because this is 0, VDD by RD is the next, this current is charging here. That's the pull-up current. When it's close to, the half point where we are calculating the delay, the voltage here is VDD by 2 and the charging current is VDD minus VDD by 2 divided by RD. So the charging current you can see here. That's how the charging current is decreasing from initially value of VDD by RD to 0.5 VDD by RD. So what is an average pull-up current? Well, very simple, to calculate average also you have to look at how things vary. But very simple average you could say is simply add the two terms at the two extremes and do by 2. Right? So the average pull-up current you will say is 0.75. Here is 1.5, 0.75 VDD by RD. Alright, suppose I take this average pull-up current and I put it in this expression here. Average pull-up current 0.75. I get an answer which is 0.67 RDCT. Right? And if you go back and look at our accurate expression was actually taking an R and a C and looking at exponential charging and doing that. That gives us an answer of 0.69. Not bad in this case. Taking the initial charging current and the charging current when it reaches the 0.5 VDD part here, taking an average of the two, putting it here, putting it back, we get an answer which is not too bad. As I said, we are not looking for very precise quantitative answers. That's not our goal. Our goal is to capture all the important terms so that we understand where is the delay coming from, right? So this expression is fairly, for quick calculation, this expression is pretty good. All that you need to do is calculate the average current that will come from your pull-up. Find out the net capacitance at this particular node. And then you have an estimate of delay. 0.5 CT VDD by I pull-up. Very simple calculation of the average, getting a first order estimate of how much is the delay that comes from charging this particular capacitor. All right, as I said, it can be a transistor. So all that you need to do is calculate the current, initial current, calculate the current at the end, take an average, and then calculate what is the delay. All right. Now, note there's something very interesting that we can find out. If we go back in the pull-up current in the case of resistor. So in the case of a resistor, if you note, the pull-up current will obviously be dependent on VDD. In this case, if you look at it, the pull-up current is directly proportional to VDD to the power 1, right? But in general, if I replace it by some other element, you will find that pull-up current is, especially transistor, will be proportional to VDD as expected, but it will be some power of M, and M in general may be greater than 1. For a resistor, M is 1, but if it's a transistor, M will be greater than 1. You'll see that. Because note that if it's a transistor and the transistor is in saturation region, the current in saturation region is square. All right, it's a square law. So you may get something like M equal to 2, but the transistor may not always remain in saturation. It may in saturation then go into linear. So it will not be a pure M equal to 2, but it will be greater than 1. So what is the consequence of this? Consequence of this is, note that if this is VDD, capacitance on an average, let's say, it does depend on VDD, but first order, let's ignore that. So this is the VDD here, and IPU goes as VDD by M. And in general, M may be equal to or greater than 1. Normally, M will be greater than 1, as we said, except for this resistor case here. So if M is greater than 1, what you find is, in general, delay will decrease with increase in supply voltage. In this inverter. And this is true, although we are talking about inverter, remember a NAND gate is also very similar. We'll see that. NAND gate is just, you'll have pull-up and some more transistors. So similar things hold for a NAND gate. And NAND gate is a universal gate, which means that anything that you build with NAND gate will all have something similar. The delay of that particular unit would decrease with increase in supply voltage. All right, so this is in general. You can take a microprocessor, and if the microprocessor is running at 2 volt, and if you're allowed to increase the voltage, you'll find in general it can become faster. You can run it at higher speed. Bottom line is this, if you go back and look at this part, that the charging current, that's why this very simple expression, but it tells you why delay decreases with increase in supply voltage. Because the amount, as you increase the supply voltage, note that you have to supply more charge. Charge is what? 0.5 VDD times CT. That's the amount of charge that you have to supply. So as you increase the supply voltage, you have to supply more charge to the node. But the pull-up current also is dependent on VDD, and it increases faster. It doesn't increase linearly, especially if I have a transistor. So pull-up current increases faster than the amount of charge that I have to supply, and therefore the delay goes down with VDD. So very, very important point about these digital circuits is that yes, you can always, if allowed, there's a price that you have to pay. If you increase the supply voltage, we'll soon see, you'll have to pay price in terms of power and other things. But if you can increase the supply voltage, you can decrease the delay. All over, you can increase the delay by a certain percentage point. And as I said, you can imagine that if you increase VDD, then power dissipation also will increase because you're drawing current from VDD. So power dissipation will increase. So you can see a very important trade-off, which is the power delay trade-off. If you're willing to, spend a little bit more power or more power here, you can get lesser delay. Very, very important trade-off in these digital circuits here. Power delay trade-off. Delay can be decreased, but at the expense of power. At the expense of higher power dissipation. All right, so that's the trade-off that I'm talking about. Note that the limitation of a resistor is something that we can see here. If you look at this one, tau PLH is 0.5 CTD VDD by IPO. The pull-up current, if you look at it, pull-up current starts from VDD by RD and then drops to 0.5 VDD by RD. Ideally, what would you like? Once you switch this off, when you are charging this particular capacitor, if your pull-up element is capable of VDD by RD, you want it to supply VDD by RD for as long as possible. Right? So ideally, we would like this pull-up element. Let's say if I want to replace a resistor, maybe I would like it to be like a current source. Because if I have a current source of VDD by RD and it remains constant, then this particular node will charge up faster. A resistor is bad because it starts from VDD by RD and then the charging current drops to half by the time I reach here. It drops to half the value. On the other hand, if I have that transistor can act like a current source. So if I replace it by a transistor, whatever current comes in may remain constant for a long time, unlike a resistor. So resistor, you can see, is not a good pull-up element. The current is continuously decreasing, the charging current continuously decreasing here. So for that reason also resistor is not good. Okay. All right. So this was the low to high propagation delay, tau PLH. Similar arguments you can use for high to low propagation delay. So high to low propagation delay, which means that this goes from 0 to VDD here. This node is initially charged to VDD. When this is 0, this is charged to VDD here. And now you have to discharge this. So now if I go back and try to use this expression, what will I write it here? Again, I have to discharge this capacitor. So what should I write? Note that this is what will happen. If you abruptly switch the input is in blue. You go from 0 to VDD here. The output is initially 1. This is normalized voltage here. The output is initially VDD and starts to decrease. And the tau PHL will be the point where again it reaches half the value. Alright, so that's the definition. Now can you see that I can write tau PHL according to the same. Again it has to discharge by how much? 0.5 VDD. So 0.5 VDD CT. That's the amount of charge that I have to take out. In this case, I have to extract that much charge. And what is this? This is the average discharge current. Again, this current will vary with time, but if I can define it as an average discharge current. Right? This is the discharge current here. And we are talking about the tilde here is the average here. And this is also average capacitance. Average over what? Average over this range here. I'm going from VDD to VDD by 2, so it's an average capacitance over this range. And the discharge current is also average over this particular range. So if I can calculate this, then I'll be able to get high to low delay. Now discharge current, if you look at this discharge current will be equal to the IDS1, this transistor is on IDS1, minus VDD minus VD1 by RD. Because note there's a current that comes from the resistor. Whatever is the voltage at this node, there's a current that's coming in here. This current plus the discharge current add up to give rise to the transistor current, which is the transistor current. So you can see another drawback of the resistor. The pull down element is a transistor. This is what is going to discharge this particular node. The transistor is supplying IDS1, and what does the resistor do? It takes away a part of this IDS1. It takes away a part of this particular one. So full transistor current is not available to discharge it. If I didn't have a resistor, if I had a transistor, maybe when I switch this transistor on, I switch this transistor off. And therefore this will not subtract anymore. I will have the full NMOS current for discharging. So you can see the resistor is not a good element. It's always there. This element is not switching on or off. It's a passive element, always there, always connected to VDD, always supplying current. In this case, when I'm trying to discharge the capacitor here, I don't want any current to be coming from here. Any current from here is just causing a loss. Okay. So now how will I obtain the high to low delay here? So we've already seen how to calculate the capacitance, average capacitance. Let's say we have this value. So our goal is to find out what is the average discharge current. So we said, what do? You go to the first extreme, calculate the discharge current here. Okay, so note now what is happening to M1. M1, if you look at this transistor, note that the moment you switch this on, the voltage here is VDD. And this node has not yet discharged. The voltage here is also VDD. This is at VDD. Note that this is at VDD and this is also VDD. The transistor M1 is in saturation region. So it starts off with saturation region. So it will remain in saturation region till the voltage here drops to VD sat. And what is VD sat for us? If this is 3.3, saturation voltage is gate voltage minus the threshold voltage. Threshold voltage for us is 1 volt. So if this is 3.3, the saturation voltage is 2.3 volt. 3.3 minus 1. So it will remain in saturation region as this node discharges from 3.3 to 2.3. And the moment the node voltage falls below 2.3, it goes into linear region. And from 2.3 to 1.65, because we are talking about half of VDD here, 1.65, it remains in linear region. Right? So what I'm interested in is calculating what is the discharge current here and what is the discharge current here at these 2 points, and take an average. To do a very quick calculation, take an average of the current here. So the discharge current in the beginning, the transistor is in saturation region, so it's Kpn W by L. The voltage here is VDD minus VTHN square by 2. So straightforward, I can very quickly calculate once I have the size of the transistor. VDD is known, VTH is 1 volt. I can calculate what is this current. What is the discharge current at this particular point here? It's in linear region, so I use this expression here. Kpn W by L in linear region, this is the equation, VDD minus VTHN. VDD by 2 is the drain to source voltage at this point, drain to source voltage here, VDD by 2. And so VDD square by 4, this is the equation in the linear region. And this is the current that is coming from the resistor, VDD minus VDD by 2. So that's the current that's coming from resistor. So that's the current at the end of this particular phase here. So I can very easily calculate this current. I can very easily calculate this current. And as I said, it's crude, but I can take an average. This current plus this current divided by 2 and take an average current and get an estimate for the day. Okay. So this is where we are. This is this current and this is this current here. So now let me put some numbers here. We had 4 lambda by 2 lambda, 72K and all that. So I can calculate. This current comes out to be 0.53 milliamperes. We have all these values. KPN, everything is there. 0.53 milliamperes here. This value comes out to be 0.19 milliamperes. 0.53 and 0.19. So I take an average of the two. I take an average of the two and I put it here. CT, we had already done a calculation earlier. And if I do that, I get a delay of 39 picosecond. 39 picosecond here. Now, interestingly, note that high to low delay. To discharge it, the delay is 39 picosecond. Low to high delay, we had calculated earlier. To pull it up, the delay was 424 picosecond. These are the simulation results here. So note that this is the charging part of this particular node here, and this is the discharging part. You can see that high to low delays, discharge is so fast. Discharge is very fast here, but the charging is pretty slow. You can again see the limitation of the resistor. Resistor, I have to use a 72K resistor, and that's why charging is very slow. Now, we may say, well, why don't you use 10K resistor? We had seen earlier, if you use a 10K resistor, I can improve the charging, but then something else goes bad. We'll see later on. Okay, so transistor, you can see compared to a resistor, transistor is very good as a pull down element. Look at this, small size, 4 lambda by 2 lambda, and it can supply a current of 0.53 milliamperes, discharging current emission. While a resistor, I think we have resistor cannot supply current here. You can see 3.3 here, and if this is 0, 3.3 divided by 72K, and you can see resistor can supply you a current of 1 order of magnitude lower. 1 order of magnitude lower. We'll come to that discussion of transistor versus resistor later on. So you can see here, this device has very relatively low, high to low propagation delay, 39 picosecond. Very quickly the node discharges, but the delay mostly comes from the low to high delay, which is 424 picosecond. All right. So for delay analysis and understanding, we'll use this particular equation here. Tau P, whether it's HL or LH, 0.5, CT VDD, this term will remain constant. If it's high to low, we'll use a discharge current. If it's low to high, we'll use a pull-up current, charging current here. And this will give us an estimate of how much is the... Now, 39 picosecond we get from here, and from here is not too off. If it's 39 here, from accurate calculation, it will give you 25 or something like that. So first order calculation, these are good, reasonable numbers to get here. Okay. And all right, so that's as far as delay is concerned. Let's look at the power, because we've seen that anything, if you want to improve delay, you'll have to change things here, and the other thing that gets affected is power here. So if you look at power dissipation, extremely important. In fact, most modern digital systems are ultimately limited by power. Power is the main limitation because of mobile applications, and battery is very, very important. Battery with limitations with its this thing here. So they're ultimately limited. You can't go to very high speed. Theoretically, you can build much better, higher circuits with higher delay, but you don't do that, because with higher performance comes higher dissipation, and you can't manage dissipation. In fact, I think if you look at microprocessor speeds, the Intel cores 2.4 gigahertz or whatever, you look at the clock frequency, right? Maybe go ahead and look at clock frequencies, how clock frequencies has been improving. And somewhere around the time, I think somewhere you'll see the clock frequency increase to 2.4, 2.5. It's not increasing. Clock frequency probably has saturated. It's not increasing. Why are they not increasing the clock frequency? As you increase the clock frequency, more dissipation occurs. You can't manage it. You can't extract the heat. Now, how is the heat related to clock frequency? Well, you'll see it here in this simple discussion here, which will illustrate what is the relationship between the frequency that I'm talking about and the power dissipation here. So there are two kinds of power dissipation. One is what we call a static, and the other one is dynamic. Now, let's understand. Static means the following: that I've applied, let's say, a 0. I've applied a 0 here, which is, let's say, ground. And the system, 0 is there, and that's it. 0 is there. And note that if this is 0, transistor is off. And ideally, I will have no current coming. No current is coming through because the transistor is off. So no current. But in reality, transistor is not off. There are two kinds of currents. When we get time, we'll see. There are two kinds of currents which are still flowing. Even though you apply 0 here and 0 here, there are two kinds of current that is coming. One is a current which is flowing from drain to source. Even though the transistor, you have applied 0 volt, there's a current coming here, leakage current here. And in modern transistors, what has happened is that the gate oxide has become very, very thin. Very thin, a nanometer. Extremely thin. So the leakage through the gate may also be there. So, you see here, this is 0. And I mean, if very little current flows, this node is at VDD here. And think about it. If you have 3 volt across 1 nanometer device, what would happen? 1 nanometer thickness. 3 volts across 1 nanometer. The field across that oxide will become very high, will exceed the breakdown voltage of the oxide, and this would be leaking. So in fact, I can't, for these modern transistors, 3.3 is very high. You can't apply 3.3. They'll work with 1 volt. That's it. You can't go to 2 volt. 2 volt, if you put here, the gate oxide will break down. It's so thin that, now you may be wondering, why is it so thin? Why are you making it so thin? Okay, so we'll come to that later on. Why are you making it so thin? Why don't you make 10 nanometer, 100 nanometer? Okay, then the transistor doesn't work properly. Right, so there are reasons. But what I'm trying to point out is, when I apply a 0 here, ideally, the MOS transistor does not have much leakage, but in practice, the leakage current is there. And so there is a power dissipation, but maybe small power dissipation if you manage it properly here. If you design your transistors properly, maybe small here. So this is okay. When you apply a 0, not that much power here. But when you apply a 1, so P is VDD into I leakage. Whatever leakage current flows, the power that is being dissipated is here. When you apply a 1 here, VDD here, now the transistor is on. Transistor is on, and the voltage here is very close to 0. And so the dissipation is VDD squared by RT. So there is, note that I've applied VDD and I've kept it at VDD. There's a continuous power drain. Continuous power drain of VDD squared by RT. And this is what is very bad about a resistor here. Now, when we design, in digital circuits, the idea is the following. In digital circuit, what matters is that if you look at all these nodes, what matters is to change the state of the node. If it is 0, you may be wanting to change it to 1, whatever, depending on the functionality. If it is 1, you're wanting to change the state to 0. So in some sense, I'm interested in changing the state of the nodes. And therefore, I should draw, the idea is that I should take power from my supply only when I want to change the state of the node. When I'm doing some work. Work is changing the state of the node, taking it from 0 to VDD or VDD to 0. So the idea is that only if you are doing some work, only if you are changing the state of the node, then only you should take the power from the supply. In this case, note that this particular node, when you apply VDD, this particular node goes to 0. After that is 0, you're not doing anything to that node. It's 0 continuously, and you keep on drawing power here. That's a very bad state of the affairs. I'm not doing anything. The node is at 0. And it continuously drawing power from the supply. That's horrible. So you don't want that at all. So this is what I mean by static power dissipation. That when static in what sense? I'm not changing the state of the node here. The node is now gone to VDD. This node is whatever at 0. This node is whatever 0. This is at VDD. These are stable. And under those stable conditions, are they taking power from the supply? Whatever power they're taking from the supply, we'll call that as the static power dissipation. When the nodes are not changing, discharging, charging. That's the static power dissipation. We don't want static power dissipation at all. But this circuit has a major problem. It has a static power dissipation. When my transistor is in 0 output state. When the output is 0, close to 0, logic 0, it consumes power. That's totally bad. So the other power dissipation is, as I said, power which is required to change the state of the node. That's what we call as dynamic, because of the changing part here, dynamic. And so this is the power. Let's try and understand this here. So as I said, one of the principles that you should keep in mind is energy should be drawn only to change the state. Otherwise, you should not take up any energy from anywhere. Right? So that's the bottom line. Okay. Now, let's talk about dynamic power dissipation. Now, I want this discussion to be more general, so I'm going to replace this by some pull-up element. Doesn't really matter what it is. Okay. So now what happens is, note that when I go from VDD to 0, so this goes to 0 here, transistor turns off, and as we just said, a current flows here to charge the capacitor. Now the current that flows to charge the capacitor, the current is coming from VDD. And a current coming from VDD means what? You're taking energy from the battery. Let's say this is your battery, you're drawing energy from the battery. Where is that energy going? Are you seeing that I have switched this off? I abruptly apply VDD to 0. This transistor is off, fine, gone. Now this capacitor is charging. And it will charge from 0 to eventually to VDD. And as it charges, it draws a current. And therefore it draws energy. How much energy does it draw from the supply? Let's calculate that very quickly. We can calculate. Energy drawn from the supply is VDD into I pull up into dt. V into I is power. Power multiplied by dt integrated over the entire period here from here to here. And that you can clearly see is CT into VDD square. Because IPU into dt is what? Is the total charge supplied. IPU dt integrated over the whole thing is the total charge supplied here. And the charge is nothing but CT times VDD. And so this is the energy that I took from the supply. Where did that energy go? Well, half of it went in, is stored here. Half of it is actually dissipated in the resistor, and the other half is stored in the capacitor. We know that half is half CV square stored here and half is here. Note that I did this calculation without talking about what is there in pull-up. It may be a resistor, it may be a transistor, half of it will be dissipated here. It doesn't matter whether the value is 72K or 32K or whatever, it doesn't matter. It's independent. Very interestingly, it's independent of what you connect here. You can connect anything here. Half the power, half the energy is going to be dissipated here in this particular element. Alright, so that's as far as charging is concerned. So every time you charge a node, what do you lose? How much energy do you lose? Half CT VDD square. Every time you charge a node, you lose half CT VDD. Very general statement. Every charging of the node, when you go from 0 to VDD, you're losing half CT VDD square. Because who's going to charge? Something here will charge. Something here will charge. Right? And therefore, half CT VDD square will be lost. Now, fine. When this inverter switches, now at some point this will be discharged also. And when it discharges, whatever you stored on the capacitor, that also is lost. That also goes away. So every time you discharge a node, what do you lose? You again lose half CT VDD square. So this is the thing that you have to keep in mind. Every time you charge a node, you lose in energy half CT VDD square. Every time you discharge a node, you lose half CT VDD square. So the total, if I continuously apply to my inverter like this, right? So this transition will cost me how much energy? Half CT VDD square. Because when you go from here to here, this has to fall from whatever. And when you go from here to here, you again lose half CT VDD square. So how much energy do you draw in one clock cycle? CT VDD square. So what is the power which is dissipated here? So 0.5 CT VDD square for this transition, 0.5 CT VDD square for this transition, and in one clock period, so the power dissipated, this energy plus this energy divided by 2. So power dissipated is CT VDD square into F. This is what we call as dynamic power dissipation. To switch a node from 0 to 1 and 1 to 0, you need power. You need energy to cause a change in the state. From 0 to 1 and 1 to 0. And depending on how rapidly you are switching a node, that's where the frequency comes in. How rapidly are you switching the node? If you switch it very fast, you need more power. You need more power here. So you can clearly see, so if we were talking about a microprocessor, why can't I increase the clock speed of the microprocessor? Well, if you increase the clock speed of a microprocessor and you have a 100 million transistor circuit, imagine how many nodes are there in that 100 million transistor circuit. Now, every node will, of course, not switch. Some nodes will switch, some may not switch here. So a fraction of nodes will switch. So all those switching of the nodes, you can imagine how much will be the power dissipation. So the bulk of power dissipation in all these digital circuits come from switching of the nodes. You have to switch the node on, off, 0 to 1, 1 to 0, 0 to 1, 1 to 0. All that power is coming from. Right? So this is what we call as the dynamic power dissipation. CT VDD square into F here. That's the note. Now this is pretty bad. Why? Because you remember what we said, you want to increase the delay. Reduce the delay. What do you do? Increase the supply voltage, right? And if you increase the supply voltage, the delay would reduce. But what would happen to the power? Increases a square of that. VDD square. So delay will not decrease with 1 over VDD square. Delay is not reducing as 1 over VDD square. Because go back and look at the delay. We wrote down the expression. How will delay increase? If you go back somewhere here, we said, look at here. So even if the I pull up is, let's say, VDD to the power 2, VDD to the power 2, delay will reduce as 1 over VDD. 1 over VDD. So you can reduce the delay, but what happens to the power? Power increases as VDD square. So what is killing the modern digital design is the power. Yes, you can reduce the delay, do things, but I can't manage the power. And especially for all these mobile, if I have a big computer and I can build heat sinks and I can do water cooling and all kinds of things I can do, to cool. You have all these server farms where everything, Google and all that have their server farms. And the server farms and all that are, they have special cooling, water cooling or air cooling or whatever. They're even setting up in Scandinavian countries where naturally it is cold. The environment is cold. So, all these server farms, it's easy to cool, maintain temperature. But the mobile that you carry, server farms can be put there, but what about the mobile? Mobile you carry in your pocket. And how do you dissipate the heat? So that is the most crucial parameter right now. How do you manage the power dissipation? And the heat which is generated here, how do you extract it out? So that has become the key limitation of many of these designs here. And so some of these, the more complicated things that are there, the principle behind these are in these simple equations here. In these simple equations that you see. Why is there dissipation? Where is the power being dissipated? It's all due to these nodes being charged and discharged. All right. So we said that, if I look at any typical node in my digital circuit, except for, I have a clock, and the clock is running all along my whole chip. And except for the clock, wherever the clock is actually going, that particular node is switching at clock frequency. Right? That particular node which is directly connected to clock is switching at clock frequency. Most of the nodes would not be switching at that frequency. Sometimes they would be switching, sometimes they would be dormant. Then again some signal comes and they'll start switching, again they'll be dormant. So for a particular node, I cannot simply put an F there, clock frequency. So what we need to do is take F and multiply it by what we call as the activity level of a node. How active is a node? So the nodes which are directly connected to clock, their activity level is, maybe 1, let's say. So you get an expression CT VDD square F, but I need to multiply it by activity level. Some nodes may not be switching that high, so activity level is low. And at some nodes, the activity level may be very high. So they would be consuming a lot more power. So power is again not uniformly distributed. Some nodes are very active and a lot of power there. Some nodes are not that active, less power here. So power is all, you need to get so in modern design, you need to get a full temperature map of the IC. Where are power being dissipated here? And you have to balance maybe, to lay out things so that you don't get hot spots. Some places getting, a lot of power is being dissipated. You'll have to manage how the power is sort of distributed here. Okay, so let's stop here. We'll carry this discussion then in the next lecture.